Hi everyone. So tonight I want to talk a little bit about forecasting an election and particularly how to do so using something called Monte Carlo simulation. And I think it's a great example to use in this class, especially early on, because it shows that we can really learn some very deep aspects of how to simulate things computationally without needing to code a single line of code. And I'll use pseudocode to describe our ideas throughout this lecture, but it will we'll be able to do quite a bit in terms of planning the code and thinking through how we're going to execute, finding an answer to a practical question. And so much was written about, I think it's safe to say, in the 2016 election. There was an enormous amount of media coverage, to be sure. And one of the big areas was in election forecasting. So here are two different media outlets, 538 and New York Times. And they both had election simulators that would forecast the election at a given time based on data they had access to at that time. And you'll note that the final predictions of each of these was a little bit different. So New York Times was more confident in a Clinton victory. 538 was a little less confident. And I would point out as well that just because the forecast was incorrect in the end result doesn't necessarily mean that the idea of making a prediction or assigning a percentage to it on the election day is flawed. So we'll have certain things that we're not 100% certain of. And a U.S. presidential election is certainly one of those things, leading up to the moment at which the votes are counted. There are some patterns here, though, and the patterns are the same for both of these media outlets. So I want you to note, of course, that the projections tend to fluctuate over time, but they do have the same shape. You can see a rise and a fall that correspond to roughly the same times. And there are reasons for that. So you have news events that may take place that will swing polls in favor of one candidate or another. And you have things like conventions where one candidate will receive more coverage around that time, and that will cause the polls to move in a certain direction. But ultimately, polling data is going to be inherently volatile. So when you see a poll, and the polling data is going to be what we use in order to build one of these simulations, there is always going to be a margin for error quoted with the poll. So we could look at a different poll, whether it's a election poll or whether it's a presidential approval rating. Those polls always sample some small subset of a population, and so as a result, they acknowledge that extrapolating over the entire population will be difficult, and the poll is reported with a margin of error. So this is a percentage value that, to some confidence, say 90% confidence, within which we are going to have that certain amount of confidence within the poll. And so for something like this particular presidential approval rating, we have a 4% approval rating, or 4% interval, so margin of error within the poll. And you can see that. So there's an 8% spread, 4% on either side of this chart, where at any given time, we may be 90% sure that the true number, whatever it is, if we were able to poll every American in this case, would be within 4% of the stated number. And so they would make this difficult in that we're never going to have a true number of, in a given area or across an entire nation, what people think, even with only two options. And so I should note, for folks who are not in the U.S. are familiar with how the U.S. presidential election works, it employs this Electoral College where there is a winner-take-all in the states. It's even a bit more complicated than that because you have certain areas, say Nebraska and Maine, that are divided further. But most states have an election. Whoever wins the most votes takes all of the representatives from that state. And this is based on the number of representatives in Congress and the Senate that a state has. And then that state will then form electors from the winning candidate's party, and they go and cast votes. It's actually not a guarantee that the electors will cast the votes that they've been asked to cast. That's another quirk of the system. And so in 2016, there were actually a record number of defectors within the Electoral College, or people who switched the vote that their party had asked them to make, or that the electors in the state had asked, the populace in the state had asked them to make. And so there were 7 switches at the time of the voting, but it didn't change the overall outcome. So the idea that we want to employ is to simulate the election many times using the state polling data. So this is what an outlet like 538 did. And you'll notice that in these, there's a bar chart for a given number of electoral votes with kind of a height of the chart. And the height of the chart will represent the frequency or the number of elections over many simulations that the given candidate will receive that exact number of votes. And you'll notice that these, for Clinton and Trump, are mirror images of each other. And that's because the number of votes will always add to 538, hence the name. And so if one candidate receives 358 votes, then the other candidate will receive 180 votes. And so that particular simulation where we have 358 over here, then we would have 180 on the other side. And so that's why you have kind of a mirror image of these two plots. And so how the idea works is to simulate the election many times using the data that we have in terms of polls, and then to produce a percentage based on the percentage of time, percentage of simulations, I should say, that one of the candidates wins, and that will represent their forecasted probability of winning the election. And so how this works is to use a much more general idea called Monte Carlo simulation, where we run random simulations repeatedly in order to obtain an approximation or an estimate of what we want as the result. And so, for example, if we were simulating stock prices, for example, we would want to build in some noise. And so there's a certain amount of this bounce in a stock price that will reflect what the market feels is the valuation of the company. And so if something is going up quite a bit, 200% and then dropping to 25% of its value, then that's market factors are at play there. But if we were to zoom in far enough on this, we would see a lot of little bouncing in the stock price. And so we want to have a process that allows for these types of almost random bounces back and forth in the stock if we wanted to simulate the price of the stock over time. You have another example, Monte Carlo simulation, where if a weather forecast says that it's forecasted for rain with 60% probability, that means that they ran simulations, and in about 60% of the simulations, they found that it was going to rain on a given day. And a more advanced model would produce something like a snowfall chart, or would estimate the probability of a hurricane hitting a certain area, or so on. Another example, so something from, say, sports. You could imagine that we could run many simulations of sporting events and use this to help us build a daily fantasy lineup or make wagers on sporting events. There's even an interesting example of Monte Carlo simulation with respect to elections, which is that if we look at, say, where I am currently, Pennsylvania, we look at the Pennsylvania congressional districts for sending representatives to Congress, then the districts have an approximately equal number of people, but they can be drawn in ways that the state sees fit at the time. And so you could look at one district which in 1952 had a pretty, relatively round, contiguous shape to it. And over time it's changed until what we saw in 2013, which was far from a tightly formed convex shape. And when we rotate it a little, we can see, what is it that this even looks like. Someone came up with Goofy kicking Donald Duck, which is a good description, and the kind of thing that once you see it, it's difficult not to see when you look at this congressional district. So the way that this was addressed when a lawsuit came up and then the Pennsylvania Supreme Court reviewed the case was they asked, well, just because the districts are strangely shaped doesn't necessarily mean that it's gerrymandering. It doesn't necessarily mean that it's one party that has rigged the state's districts to look in a certain way so that they'll maximize their number of seats. And actually, a Carnegie Mellon colleague in the mathematics department, so a professor in our science college, looked at this problem and testified, running trillions of simulations and looking at how often the simulations were as unfair as the reality, and saw that in only a very small fraction of cases would a random result have produced districts that were as of equal unfairness to the districts that we have in practice. And so that result led to a Supreme Court decision where the Supreme Court of the state actually drew the districts themselves once again. So we moved from these wacky districts in 2016 to districts that look a little more normally shaped for the 2018 election, and the results of the election kind of bore out that one party had more unfair representation and gained seats as a result. So this type of thing is everywhere. We want to do it with respect to a US presidential election, but it's a very powerful tool. And I want us to dig into the details of how it works in any programming language. And the details that often, if I can appeal to the manifesto or the central theme of this course, that are far more general than a specific language, but that will occur and that are vital details to know about how it is that we implement a random simulation on a basic level that will give us a really powerful appreciation of this Monte Carlo simulation. So where I would like to start is with a slightly simpler example than building an election simulator, and to look at something that would take the Monte Carlo analogy to the casino at Monte Carlo and look at a casino-based example where we want to compute the house edge of a game of chance. So the house edge would be the average result per dollar wagered that the casino is going to win on a game of chance. It could be that they're going to lose on average, but casinos wouldn't be in business likely if that were the case. And so, for example, one way that we could run Monte Carlo simulations would be to try lots of different strategies for playing blackjack based off of what the player's hand is and what the dealer's showing card is, to give us a sense of whether or not we should stand or hit or double down or split. And so we could produce this table that has kind of ideal strategy based off of, minimizing the house's advantage. If we produced a table like that and we had a fixed strategy, we might stop for a second and think how it is that we could compute the house edge of a game. And the answer would be, well, we could fix a strategy, and for that fixed strategy, so say for this strategy of blackjack, we could simulate a computer to play that game a number of times, or over a number of trials, and then simply divide the amount lost by the number of trials. So we could play the game 1 billion times, take a very large number of n, with the presumption that the house edge will be kind of the average case behavior, and that many simulations will allow us to produce this. So I'll look at an even simpler game, which is a type of game called a binary game, where you only have 2 outcomes of equal and opposite payouts. So, for example, the player will win $1 or lose $1 based on wagering $1. So they either wager $1 and lose it, or they wager $1 and they get back a certain amount, which in the simplest case is their $1 plus an additional $1. And something like blackjack isn't binary because you have payouts that depend on the outcome. If you get a blackjack, then you get paid a little more than your original $1 back. There are options to gamble more or wager more as you go through the game. And it's also harder to simulate because I would need a fixed table of decisions, and it doesn't represent kind of the complexity of the game because the player can make many different decisions, even though it's a game of chance. So we might look at what would be a suitable binary game. And a very simple one would be something like rock, paper, scissors, although in theory, the house edge or something like that would be 0 because it's essentially a coin flip every time. So we want something in between the sophistication there. And I'm going to pick the game of craps, which actually does have variable payouts, but can be formulated in a simple form from the person who's rolling the dice's perspective. And if you're not familiar with the game, I'm going to just briefly review the rules. So the roller can roll 2 fair dice, and if they're betting on themselves, which usually is the case, and the dice show a 7 or 11, that's an instant win. And so that you would get back your dollar wagered plus an additional $1. If the dice show a 2, 3, or a 12, you would lose. And then in all other cases, so you roll a 10 or a 6, then call that number X. And then you're going to continue rolling. And now you want to roll an X. So if I've rolled a 10 on my first roll, I want to keep rolling and try to hit a 10. Now 7 goes from a winning number to a losing number, and everything else means keep rolling. So if I rolled a 10 initially, I'm going to just keep rolling the dice until I hit either a 10 or a 7. A 10 would be a winner, 7 would be a loser. And we can actually write out pseudocode for computing the house edge of a game like craps. We could say, well, take some count variable, initialize it to 0, and then for, say, an integer that ranges from 0 up to num trials minus 1, or a simpler way of saying that is, for, say, num trials total trials, let's play the game once, and I could sub in a different binary game here, but I'll have a subroutine, for example, called play craps once, and that's going to return true or false. So if that outcome, I can store that in a variable, if that outcome is equal to true, well, I'm going to consider that a win, and I'm going to increase the amount of money that I've won, which is what count is holding, by 1. So I'm kind of starting count at 0, saying this is the amount of money that I've won or lost. And if the outcome of playing craps once is false, well, I'm considering that a loss, and so I'm going to subtract 1 from count and store that back in the count variable. And so, my money won or lost is going to go up or down over time, and at the end we're going to return however much that I've won in total, divided by the number of trials that we've played the game. And we could slow down and say, well, there's no randomization in that function. So we could look and say, where exactly is it that it's hiding? And well, if it's not in this function, it must be in that play craps once subroutine. And this is an illustration of something that we'll see multiple times throughout the course, which is that often the details are buried within subroutines, and that actually can help us write code because we're not worried about details at the start. Here, we have a high-level function that says, well, I want to compute the house edge. That means I need to play a game, say, n times. The easiest way to do that is to have a for loop that does something n times and pass playing the game once to a subroutine. And I would note again, you could compute the house edge of any binary game. Just replace play craps once with play whatever the game is. So I'd need to make a very minor modification to this. I could even take a separate parameter to this function and have multiple games that I'm playing depending on what that parameter is. So I would pause for a second and say, on the level of pseudocode, maybe give a shot to writing this function play craps once. I will allow you to assume a sum 2 dice subroutine. So I'm going to pass the details again of the randomization to another subroutine, and I'm going to assume that I have a subroutine that's going to not necessarily need to take any inputs, but that will produce the sum of 2 randomly rolled dice within the computer. So however that process is going to happen, let's assume that it's written for us. If we assume that we have a function, it'll return a number between 2 and 12 based off of the outcome of some 2 dice. And I'll discuss that function, but I'll pause here for a second and allow you to take a shot at how it is that we would convert the rules of craps that are shown here to a function called play craps once that will produce true or false based off of the outcome of playing this game. Okay, I'll let you give that a shot. So the key to solving this question would be to use our sum 2 dice subroutine and create a variable that is equal to calling that function, and that could represent the result of our first roll. So I called that x, I could call it first roll, and then we could check whether or not it's 7 or 11 or 2 or 3 or 12, and those are the easy cases because then it's just a single roll. And then otherwise I have to do the continued rolls, so a loop is in order here. And then the question becomes, well, what the test is, what it is that we're doing. And that's really the challenge of this question. Once we see it, then we're going to be okay. So again, I set first roll equal to the value of sum 2 dice returning the sum of 2 dice. I could check if first roll is 2, 3, or 12. In each of those cases, we're going to return false since that's a loss. If it's 7 or 11, we'll return true. I actually don't need the else because if I reach the else, then I know that 4, 5, 6, 8, 9, or 10 is equal to the whatever the first roll is. But I'll provide it here just for the sake of simplicity or consistency, I should say, so that we've got one case where we win, one case where we lose, and one case where we continue rolling. And so first roll will have kind of variable scope outside of this else statement because we declared it at the beginning. And so we're going to have a loop then that will continue rolling. And so the tricky thing to see here is that something like while true, an explicit loop that will continue going forever, at least theoretically, is a perfectly fine thing to do. And I always tell students, well, it's perfectly possible that someone playing craps could roll a 10 and then stand there at the table rolling the dice and never hit a 7 or a 10. But no one walks into a casino to play craps with the concern that they're going to be there for 40 years. And we shouldn't worry about this being an issue computationally too. So this is actually a theoretically infinite loop that in practice won't be, because we're going to keep, even if it's not, it won't be 50% probability even, but every time we roll the dice, we're diminishing the probability that we won't have either rolled a 7 or rolled the first roll. And so this probability is essentially going to 0 as we continue doing these rolls. And so it could take 20 rolls or so, or more, but in practice it's just a matter of waiting around until that happens. So within this while true loop, we're going to have a new roll that sums the 2 dice. And this new roll will change every time, but the first roll will not. And then we check the value of new roll against first roll. And if the new roll is equal to the first roll, then we're going to return true. That's another winner. Otherwise, if new roll is equal to 7, we're going to be a loser, so we're going to return false. And otherwise, we're not going to have an else or need to take any other action. I'm just going to leave it and then allow the loop to continue back up with setting new roll equal to sum 2 dice. So again, now that we're using kind of the fact that we can call subroutines, this principle of modularity, we can see that even something where, the craps is not the simplest game in the world, but we wind up with approximately 10 lines or so of pseudocode for representing how it is that we would simulate the process of playing it once. And we need to know a little bit about how it is that we're going to get a dice roll, or have sum the values of 2 dice. We haven't said anything about randomization, but I'm going to use this simpler craps house edge example to get at that and realize that we've got 2 goals. The main goal is, of course, to simulate a presidential election and figure out how forecasting works and kind of touch on that a bit. And we have a more modest goal, though, which is to program a computer to roll dice, because I've written, at least on a pseudocode level, the high-level functions of computing the house edge. We didn't need any randomization for that. I just need to program a computer to roll 2 dice. How hard could that be? And again, in terms of how this course can be differentiated, it's an important thing to know about. It's an important thing to appreciate that there are pitfalls in this process, especially because we may think that it's easier than it is, just because we can be quite good at thinking up random digits, or at least digits that we think are random. So I could do this myself, and just spit out random digits: 1472813308004 765, etc. And what process produced that sequence of digits? Isn't it weird that you can just kind of do this without really thinking about it? What process is going on in your brain that's allowing us to do that? What evolutionary purpose might such an ability serve? If we go back to something that I said in a previous lecture, this Dubzhansky quote that nothing in biology happens but in the light of evolution. Why might we, from an evolutionary purpose, be spending kind of fitness points on needing to generate random digits? The example I always come up with is, well, if you're running away from a tiger in the jungle and you have a choice as to whether or not you can kind of jump up a rock and scramble away or jump down into a stream and try and swim away, you're not going to survive in any case if you sit there and try to prove mathematical theorems about which choice you're going to take. And so randomization built in, especially if it allows not just two different individuals to make a different choice, but the same individual to make possibly different choices depending on essentially randomization or some close to random process that's going on in their brain, could actually serve a positive evolutionary purpose to foil predators, for example, who will not be able to discern a pattern in a prey's movement. So it's a tricky problem. Just because we can naturally do it doesn't mean that it's not tricky. And the state of the art for generating random numbers in the 1940s was a book that was printed with 1 million digits. And so if you wanted random digits or random numbers of some kind, maybe 3-digit random numbers, for example, then you could just open the book to some point and start reading out books. That was the state of the art, like the forefront of research. And they actually did this by simulating. They had an electronic simulation of a roulette wheel, and they divided the values that the roulette wheel could have into 10 equally sized or approximately equally sized buckets. And then there were a few values that they would just throw out and they wouldn't produce a digit. But for the other ones, they had 10 equally sized buckets, and then whichever bucket that ball fell into, then they would produce a 0 or a 1 or a 2 or a 3 and so on. So this was, at the time, the state of the art. And there was the state of the art supercomputer at the time was something called, I guess in the late 40s, was something called the ENIAC computer. So this was at the University of Pennsylvania. Took up an entire room. I believe had far less computing power than the smartphone of today, but was at the time used to, or was built for missile targeting systems and kind of nuclear armament, and in the whole Cold War era. And this was something that John von Neumann, who's somebody who will come up a few times in our course, had access to and was kind of working with the government on. And his thinking was, yes, we've got a missile targeting supercomputer, and partly because there was an application of this with respect to nuclear arms, was that generating random digits is this general idea, and there must be a faster way of doing this using our state-of-the-art supercomputer rather than having to essentially play roulette 1 million times. And so he had an idea called the middle square idea. And the way that approach works was to say, well, say that we're generating 6-digit random numbers at a time. And so I could start with some random number. In this case, it's say 675248. That would be called the seed, because you'll need to start the process somewhere. And that starting process is called the seed, fittingly. And we could square that number, and if we square a 6-digit number, it's going to give us a 12-digit number. We may need to add some zeros to the left side of that if we had a small seed. In general, if we square an n-digit number, we're going to get a 2 n-digit number. And then if we look at the middle n digits, in this case the middle 6 digits, after we do that squaring, there may not be a discernible pattern between the original seed and that next set of 6 digits. And so that would become our first not random number generated, but seemingly random number that would be generated by this process. And so whenever you hear the word random number generation, it's very critical to me to dispel you of the notion that we are truly generating random numbers. It's important to have the word pseudo at the front of this, meaning that they're not truly random, but we're trying to produce numbers through a process that's deterministic or controlled that will generate numbers that mimic randomness, or that so that to an external observer, the sequence of numbers generated seems random. And the other important component of this is that we have to start this process somewhere. It doesn't just appear out of thin air. And so we have to start with some number, which in this case is 675248, but in general is called a seed. And before continuing, I would slow down for a second for us to reflect on whether or not this particular PRNG, pseudo-random number generator, is good, as well as to think about what is it that makes a good PRNG? What is it that we would hope that if we're writing a pseudo-random number generator and implementing it on a computer, what would make a PRNG good, right? And does this particular PRNG, this middle square approach from von Neumann, does it satisfy what we would imagine to be good? And I could give a specific example to maybe illustrate this. So why don't you start with the 4-digit seed of 1,600? And so we're going to square that to be an 8-digit number and then take the middle 4 digits. And I'll pause just for a couple minutes to allow you to play around with this and see what you find are the first few numbers that are generated as part of this process. A really bad one would be if we just started with a seed of 0, or at some point wound up with a seed of 0, because then 0 squared is 0 and the middle digits are all going to be 0, and so we're going to just get 0 squared all the time. Of course, we potentially could divert away from that and pick some other starting point after we hit 0, and then we would say, well, how do we pick the starting point? Shouldn't it be random? And then we're back where we started. But the problem for this is even worse. So for something like 1600, which seems fine, I could square that and I get this number. And then the middle 4 digits there are 5600, so I square that and I got 31,360,000. 3600 is the middle 4 digits, so I square and I get 12,960,000. And then I take the middle 4 digits and I square those. And I get this number, 92,160,000, after squaring 9600, and then the middle 4 digits are 1600. So I've produced this cycle where I'm always going to just keep going 1600, 5600, 3600, 9600. And so one of the things that we would be looking for in a PRNG is that regardless of what seed we choose, we would hope that we would get a uniform possibility of all the different numbers that we could generate. And so here we're only going to get four-digit numbers, and this is horrible. And here's an even worse one. So I said 0 was one where we just keep hitting 0, but 3792, if we square that, we get 14,379,264, which happens to have 3792 as the middle four digits. So we would never actually generate any numbers. And then you think about, well, there's even more to this, because I wouldn't mind to generate numbers that I've seen already. That's not necessarily a bad thing. So in my random sequence of numbers, if I'm not generating things I've already seen, then it's not truly random. If you roll a die, there's a chance you're going to get a 1 and then a 1 and then another 1. There's nothing wrong saying that you need to make this very well spread out, right? And so that would be a potential problem with something like this too. And von Neumann had a huge impact on a number of different fields, not just blowing people up, but things that we're going to see later on in the class about the fundamentals of computing. And he has a famous quote here where he says, anybody who considers arithmetical methods of producing random digits, that is, methods that are based off of addition, subtraction, multiplication, division, squaring numbers, and so on, anybody who considers doing that is, of course, in a state of sin, for as has been pointed out several times, there is no such thing as a random number. Even those numbers that seem random in my head, they're not based off of a random process. There's something going on based off of firing neurons that's bringing me to those numbers. So we can at least get better ones, though. So one might be to look at something like, so the Fibonacci numbers are formed as 1, 1, 2, 3, 5, 8, 13, and so on, where we take the sum of the previous two elements in the sequence to get the current element. And so a Fibonacci number generator might take the remainder after we sum the previous two elements. So for example, if I generated, if I chose the Fibonacci sequence, and I looked at the 30th Fibonacci number and the 31st Fibonacci number, so 832040 and 1346269, and I added those together and took the remainder when I divided by 1,000,000, well, I'd get this number 178309, and this seems nice because there's not any clear connection between the number that we produce, 178309, and the two previous ones. You might stop and ask whether or not there are any issues with this, whether or not there might be something predictable about it. And in this case, well, I could say there is a problem, which is that if you have two small numbers, or two numbers that are, say, less than 500,000, it will be very easy to know what the next element is. And in particular, it's because the process is so straightforward. Once I've seen two numbers, it will be easy for me to predict the next one. So, for example, if the previous two numbers were 100 and 200, and I'm taking the remainder when dividing by 1,000,000, well, 100 plus 200 is 300, and the remainder is 300. So we could use this idea, though, and build something a little bit more sophisticated by looking farther back than just the previous two numbers. So I don't want to look at fn-1 and fn-2, but I could look back at fn-j and fn-k. And I dislike in general pointing to any specific language when I do these theory-type lectures, but I would at least mention that the built-in pseudorandom number generator that a language like Go uses is a lagged Fibonacci generator with j equal to 273 and k equal to 607. So when it's generating a number, it looks back 273 spots and 607 spots, adds those two numbers together, and then takes the remainder when we divide by this 2 to the 31. So it's hackable from the perspective of you can use the fact that you know this is how the number generator works in order to make predictions about the numbers that Go is going to tell you are seemingly random, which are anything but. There's a more sophisticated one for this particular language in the crypto-rand package. Will have a little bit more computational overhead and take a little bit longer to run. But if you're trying to build something that is truly apparently random that even a supercomputer probably couldn't hack and figure out what the next number that's going to be generated is, then you could import this package. And other languages will have that capability as well. In fact, there's a German Information Science Institute that laid this out and said, well, what is it that if we're looking at levels of PRNGs, what makes them good? And that we can look at, the initial level and then what's the strongest layer of a PRNG. And the first thing we'd come up with would be to say, well, if I look at two different sequences that the PRNG generates, they should look different. I shouldn't see any patterns that arise over time. Those are the kind of most rudimentary approaches. If you start seeing patterns between multiple sequences of integers or numbers or whatever that we're generating from the PRNG. Level 2 would be to say that the numbers that you're generating have the same mathematical or statistical properties that they would have if they truly were random. So for example, how often a number repeats, but not how often you see the same number twice, but maybe the same number k times, or the number of times that you see a certain substring. That those are going to be, the distributed in a way that would reflect what would happen if we were looking at a truly random sequence. The third level would be, well, you could even have these two levels and a hacker could still be able to predict it. Just because it has the properties of random number generation doesn't mean that it actually is, or that it approximates it. And the hacker still could apply some approach to predict future numbers based off of the sequence of numbers that they're given. But level 4, which is kind of like the state of the art for PRNGs, would be that you can't use the sequence of numbers to generate any previous numbers either. So not only can you not predict the future, but you can't predict any previous numbers either. And that would be a very, very good PRNG. And if you want to know how is it that these work, well, another main theme of the course is that if we really want a good PRNG, we have to get very mathematically dense. And so there's a lot of very technical, like PhD level mathematical details behind how this works. And in practice, we're just going to be glad that the details are handled. But it's not, it doesn't mean that it's not worthwhile to understand that this is a challenging problem and something that very clever people have struggled with. So it's even still relevant today. So there is, for example, from a couple years ago, there was a story of casino hackers who were looking at one particular brand of slot machines where they were able to predict. So I suppose they felt it wasn't a level 3 PRNG because they could predict based off of a certain number of trials of the slot machine what the future results of the slot machine were going to be. So allegedly there was a syndicate based in St. Petersburg of people who were traveling around the globe to different casinos where they knew that the casino had this particular type of slot machine, and they would surreptitiously video the slot machine, and that would be transmitted back to home base, and that would give them enough to be able to predict kind of where in the sequence that PRNG was for generating the digits that are needed internally for the slot machine. And so then you had peculiar behavior because you had the players of the slot machines would be holding their hands over the the stop button on the spin, or the spin button, to kind of can make the machine spin the dials, and they were clicking at a very given specific time, which is strange because most people play a slot machine they'll just hit it. There's nothing about the timing that seems relevant to your average slot machine player, and the reason why was because they had been providing the enough digits so that the people centrally could run it through an algorithm and predict what the sequence of PRNG, sequence of digits generated internally were going to be. And then they would predict at what point the machine was going to pay out, not a huge jackpot, but just enough to win money without drawing attention to the player, which still could have been on the order of thousands of dollars in a day. And then they would transmit a message back to their cell phone that would say vibrate a cell phone, and the player that would come through at about a quarter second before it was the time for that digit to be generated. So that would trigger kind of the player to hit the spin button, and because of the delay, which is about a quarter second between hearing kind of the vibration or feeling the vibration and hitting the button, they wouldn't get it right all the time, but at least allegedly they were getting it right a lot of the time and enough to win money in the long run on this process. Okay, so it's still relevant in 2019, and enough though about kind of the idea that generating random numbers is an impossible goal, but many languages will still have a pseudo-random number generation built in for us. And in particular, there are three functions that we very commonly use that can take us a really long way. And that will be all we need for, say, simulating craps and computing a house edge of a casino game. There's an int function that will return, and notice I'm using random in quotation marks, a seemingly random integer, at least in the range of what the integers can be stored. There will typically be a function that will return a random integer between 0 and n-1 inclusively. And then there is a random number generation that will return a random decimal, say in the range of 0 to 1. And you might pause for a second just to reflect and think which of these functions might be useful if we're going to simulate rolling a die. Whether we want to use an int function that's going to give us an integer, or an int n that'll give us a range of integers, or a float that will give us a decimal between 0 and 1. And typically students will have a favorite. They say, well, an n-sided die, why don't I just use int n? But there's multiple ways of doing this. I could use the float function as well. So for example, I could set roll equal to float if I were going to just simulate one roll. And I could divide the interval 0 to 1 up into 6 equally sized intervals. So I could take 0 to 1/6, I could take 1/6 to 2/6, and so on. And so based off of which bucket that random number generated fell into, I would return 1, 2, 3, 4, 5, or 6. So this is a little bit of a tight way of writing the pseudocode, because I say, well, generate this random decimal between 0 and 1. If it's less than a sixth, I know it's between 0 and a sixth, so I'm just going to return 1. If I make it to that else if, then I know it's not between 0 and 1/6, so I can just check that it's less than 2/6, then I'm going to return 2. If I pass those first two things, I know it's bigger than 2/6, so I just need to check whether or not it's less than 3/6, which is equal to a half, and so on. So that's one way of doing it, and we could do it with a decimal, or we could generate a random integer between 0 and 5, so that's int n of 6, and then simply add 1 to the result. So that would give me an integer between 1 and 6. Or I could generate an arbitrary integer, so just any integer, and then I could take the remainder when I divide that integer by 6. So that would give me a number between 0 and 5, integer between 0 and 5, and then I could just add 1 to it. So 3 different ways of doing this depending on which of the 3 functions that we have. And I'd pause for a second then and say, okay, great. We've got those 3 functions that are going to be typically built in or built into a package that's easy to call. Why don't I have you pause for a second and try writing a function. We could call it sum2dice. So that's the function that we wanted for crap, since we're always going to be rolling 2 dice at a time. And it's not going to take any parameters, but it's going to return the sum of 2 rolled fair dice. So we're assuming that the probability of each number coming up on each die is a sixth. And here's the table that would show us, for example, how many times in 36 we would see each of the numbers based off the 36 possibilities of, each of the 6 possibilities for each die, but times in 2 dimensions. So we wind up with 36 possibilities, which is just 6 squared. So we have all those 36 possibilities, but they fall into 11 buckets, 2 through 12. And the probability of getting a 7 is higher than the probability of getting an 8, which is higher than the probability of getting a 5, and so on. And 2 and 12 are a 1 in 36 chance. So I'll let you take a shot at writing a function like this in pseudocode. And so the mathematician looks at this and sees, well, there's 36 possibilities, 6 of them are a 7, so I know that I can roll a 7 with 2 dice with probability 6 over 36 or 1 over 6. And similarly, the probability of rolling a combined sum of 6 is 5 over 36, 5 is 4 over 36, and so on, down to 2 is 1 over 36, 12 is 1 over 36. And so we could presumably divide the interval 0 to 1 up into sub-intervals of the appropriate widths. 1/6, 5/36, we would need 2 of those, 1 for 6 and 1 for 8. 4/36, we need 2 of those, and so on. And this will get ugly quite quickly. It will be correct, but we will have to, do the math first, and then we'll need to get it right with respect to dividing it up and making sure that the sub-intervals have all the correct lengths. And so it would be very easy to incorporate a bug here, right? For example, I returned 1 if roll was less than 1/36 instead of 2. And just in that case, I would be wrong. So it would be very easy to have a bug and also a very long function. A much better approach would be to use this concept of modularity to pass the details to an even simpler function called roll die. And to say that if I want to sum 2 dice, I'm going to roll a die, and I'm going to roll an independent die, and I'm going to take the sum of those 2 results. And that's all that I need to do. So I can presumably just write a function roll die, which is a little bit easier than sum 2 dice, because I just have to roll 1 die, and then call this function twice and take the sum. I could let you pause for a moment and think about how we would generalize this to sum multiple dice. So I'll pause for 30 seconds or so. And now if I wanted to compute all these probabilities for, say, 10 dice and figure out, well, what's the probability of rolling if I have 10 fair-sided dice? What's the probability that the sum is a 34? And now if we're doing this mathematically, this is going to become very complex quickly. Whereas if I just think about it programmatically, I'm summing multiple dice, okay, I'll have a variable called s. I'm going to have n trials. For each one, I'm going to update s by adding roll die to it. And I'm going to think of this as n processes of calling my roll die subroutine. It's not going to give me exact probabilities for each of these, but I don't need them in order to produce the outcome that I want, which is the sum of dice rolls. And so at the end, I'll just return that sum. Note that we can now implement a crap simulator because I discussed how it is that we would write leveraging an existing package or existing functions for random number generation, how we would roll a single dice. And now we can roll 2 dice or multiple dice. And it's just a matter of converting this over to the programming language of our choice, which I will do in a later lecture. But we know that, once we can play craps once, we can compute the house edge, and playing craps once is just a matter of calling our sum 2 dice subroutine twice. Once for the first roll, and then again within this while loop, however many times we need it, depending on however many times we're rolling. And so we get this nice, very short, much shorter than you might have guessed, collection of functions for computing a house edge of an actual table game. And with that in mind, I want to come back to simulating the US presidential election. Something, again, that on the level of code, I'll do in a later lecture, and we'll check out what is it that we estimate from the polling data averaged on a given date that a given candidate will win the election, or that they're forecast to win as of this time with the polling data that we know. And I'm going to use the same spirit of saying, well, I'm going to do this simulation of the election n times, and so I should have a for loop that just ranges over the number of trials and simulates one election. And that type of way of thinking about programming can make us much more powerful programmers, because we're starting to realize that we can delay important details later and split out and think about what it is that we can write. And so a function like this looks complicated. I haven't said anything about the polling data themselves, but I'm going to just pass that data down to simulate one election. If you look at the pseudocode that I've provided here, the polling data are not used at all in this high-level function of simulating multiple elections. They're going to be passed down to simulating a single election. And so all this function will do is to handle the number of trials. So I'll declare 3 variables, a win count for candidate 1, a win count for candidate 2, and the number of times that we wind up with a tie in the Electoral College, which is possible and a nightmare. But it would be possible because there are 538 electoral votes that they could each get 538 over 2 electoral votes at the end, since the number's even. And then we would have a separate process. Okay, so we should account for the number of times that we have a tie as well. And then I'm going to have, for every integer, kind of between 1 and number of trials, or for num trials, total trials, I'm going to simulate a single election. And so that single election, if we think about, well, it needs to know the data and it needs to know the margin of error in our poll. So I'm going to push those into the simulation of a single election. But what am I going to obtain from simulating that election? Remember, before we saw these bar charts, when I simulate the election, I'm going to get the number of votes that each candidate got in the Electoral College. And I can check, well, which candidate got more, or were they equal? So if candidate 1 had more votes from this process, then I'm going to increase their win count by 1. If candidate 2 got more votes, I'm going to increase their win count by 1. And then otherwise I'm going to increase the number, neither one of them won, and we got this tie, so the number of ties that we have in our simulation increased by 1. And then at the very end I could return, well, if I'm forecasting a probability, I need to divide each of these by the total number of trials. So I would divide the number of times each candidate and the number of ties by the election, by the total number of trials, and at the end that's what I could return. Now, if I knew 2 of these probabilities, I'd get the third for free, since it's just 1 minus the sum, but I could be very precise and return each of these 3 probabilities. Again, I would note I haven't said anything about the structure of the polling data, so I probably should, but as we'll see often in programming, if I'm trying to do something n times, I can just pass it to a subroutine where I do it once. And so I could use, for example, 2 maps for this polling data. I could have a map where the keys are the state names and the values are the non-negative integer number of Electoral College votes corresponding to that state. And this is based off of population, so that's why you see California at the top, followed by Texas and Florida, New York, Illinois, Pennsylvania, and Ohio. And then I could have another map that would store the, I've got these backwards actually, so apologies, but the one on the left should be called electoral votes, the one on the right should be called the polls, and those indicate kind of, states are the keys, and the keys have values associated with them that are represented by the percentage of people in the poll within that state that have indicated preference for one of the candidates. Okay, and so if I know that one candidate has a polling percentage at, say in Florida, 49.1%, then I get for free that the other candidate has 50.9%. So I just subtract that from 1. So I'll have both candidate percentages if I'm assuming a 2-candidate race. Now again, that's typically the case. This can get more complicated if there ever were a 3rd candidate in a U.S. presidential election with a serious chance of winning, although that candidate in 2016 typically came out as having less than a 0.1% chance of winning. So if we assume a 2-candidate race, we can probably get a pretty reasonable simulation anyway. And so we can simulate the single election by saying, okay, I need to know these 2 maps. So I have a polls map that maps the state name to the percentage that the given candidate is polling in at that time in that state. Since it will vary widely over the states, we should do a state-by-state polling. I'm going to need to take this Electoral College votes map that maps state names to number of Electoral College votes. And then I'm going to take the margin of error that's present, and I'll assume that's the same in the polls that I have, which that's an area of potential improvement. Let's say I set the margin of error in all the polls equal to 5% or so. We can tweak that parameter later. So how will I actually simulate an election? And again, I'm going to use subroutines wherever possible, and so this may be surprisingly short, but I can say, well, let's set two variables, college votes 1 and college votes 2. Those are the values that we're eventually going to return based off of, if I've simulated the election once, how many Electoral College votes will each of these candidates get. And then I'm going to range through the polls and say, well, I'm ranging through the keys of the polls, so that's going to give me all the states. And the polling value for that state would be just polls of state, so I could create another variable if I wanted to called poll for that particular state. I'm going to need to know how many electoral votes that state has too. So I'm going to grab its electoral votes value for the state key, and I could store that in a variable called votes. And now I'm going to say, well, I can't take 49.1% as a dogmatic polling value for Florida. I need to allow for the fact that it may be that that's too high for candidate 1, it may be that it's too low for candidate 1, and so I need to, here's where I'm going to incorporate my noise. But again, I'll pass those details down and let subroutines handle them. And I haven't said anything about how I'm going to add that noise. I'm just going to say, well, certainly I'm going to need to know the margin of error, and using the polling value that I have, I'm going to combine that with the margin of error, and that's going to produce an adjusted poll. Sometimes it's going to cause the poll to go up for candidate 1. Sometimes it's going to cause it to go down for candidate 1. But that's the whole premise of building in randomization and making this Monte Carlo simulation. So as a result of adding that noise, I can then say, well, maybe it went up, maybe it went down, but for this simulation, was candidate 1 above 50% or not? If they were above 50%, let's give them, winner take all of the votes from that state, which was held in that votes variable. So I'm going to add votes to college votes 1. If after that noise was added or subtracted to the polling value, if it wound up below 0.5, I'm going to add the votes to candidate 2. And there's going to be an infinitesimally small chance that the poll will be exactly equal to 0.5. So it's not going to be a very big deal at all to give those votes to candidate 1. And so at the end, we'll return, well, because I did this simulation for every single state, where for each state I added a little bit of noise, and that noise could be up or down in different directions for different states. I'm adding that noise to each state's poll, and based off of the simulation, kind of adding to the appropriate count, whether it's candidate 1 or candidate 2 of the Electoral College votes for them in this simulation. And then at the end, I'm going to return the number of votes in the Electoral College that each candidate got, which are those college votes 1 and college votes 2 variables. So we just need to fill in the details of add noise. We've got the structure, the skeleton of this simulation completely done. You can pick your favorite programming language and convert this generic pseudocode over to it, and you should feel comfortable to do that. And then I could reflect, okay, well, how is it that we need to implement add noise? The randomization is lurking in there, but what's an appropriate way for us to add the noise into that poll? I need to somehow take the current polling value as well as the margin of error and allow it to have some bounce in it. I'll pause that just very briefly to allow you to think about it for a second. one way that students will often come up with is to say, well, maybe I could just generate some random number uniformly from the interval from the negative margin of error to the positive margin of error. So if the margin of error is 5%, I could generate some number in the interval, negative 0.05 to 0.05, and then that will allow me to go up or down. It's not going to preference one candidate, and I can simply add the polling value to that random number between negative margin of error and margin of error that I find, and that would be one way of doing it. So I could take my poll and my margin of error value, and I could generate a random decimal number between 0 and 1. So I could use that float subroutine that I mentioned before. And if I multiply it by 2, I'd get a number between 0 and 2. Subtract 1, so x equal x minus 1, I'd go down to negative 1 and 1. And now if I multiply that value by margin of error, it will be between negative margin of error and positive margin of error. Okay, so I could have done all that in one line, but I wanted to represent that as a few lines. And then so that would give me negative margin of error to margin of error, and I would simply add that value x to whatever my polling value was. And we could stop for a second and consider why that is not necessarily an ideal model. And many students will say, well, odds are if we're sampling a polling value, then it's more likely that the true value is close to that than it is that it's far away from it. So ideally, the farther away we get from this poll, the less likely it is that we're out there. And so this leads to us to try and adapt a Gaussian or a normal distribution where we have a bell shape with infinitely extending tails. So this is actually nice because we could be off by more than the margin of error. With this previous adenoise function, we were 100% of the time going to be between negative margin of error and margin of error. In practice, we could actually be outside of that. It's possible that we could have a poll at 49% with a 5% margin of error, and the true value is actually 59% for candidate 1, or 41% for candidate 1. And so we'll use this bell-shaped distribution that will allow us to have infinite tails. The probability of generating something well out there is going to be lower and lower the farther out that we go. And so here the height at position x kind of indicates what's the relative likelihood that will generate a decimal number x. So if I take a given interval underneath this curve, kind of calling back to taking an integral from calculus, but if I take in the area underneath the curve, that area under the curve compared to the entire area under the curve, which in this case is 1, is going to tell me the probability of generating a number in that interval. It's very nice. And because it's higher in the middle, any interval kind of around the center is going of the same width is going to have higher probability. So fortunately, I will have in most languages a built-in standard normal distribution number generator as part of the PRNG package. And so I could use this, so have what's called a norm float, perhaps, function that will not take any inputs but return a number from the standard normal distribution. So standard normal is centered at 0, and so it will go out from negative infinity to infinity with a 68.3% chance of the number that we produce being between negative 1 and 1, approximately 95% chance of being between negative 2 and 2, and everything kind of diminishes from there. So if we want something with, say, I don't know, a 95% chance of being between negative 1 and 1, then that will handle that, we're mostly within our margin of error, and so we have, that 95% confidence that it's within the margin of error, and so we could pick some random number from the standard normal. We could divide it by 2, so that would give us, if the original number would have a 95% chance of being between negative 2 and 2, if we divide it by 2, that's going to give us a 95% chance of being between negative 1 and 1. And now I multiply that by the margin of error, and I have a 95% chance of being within, or I have a 95% chance of being within negative margin of error and margin of error. So I go from -1 to 1 to negative margin of error to margin of error, and then now I have an actual margin of error value that could change depending on this margin of error parameter. Maybe it's 0.05, in which case it's 95% chance of being between -0.05 and 0.05, or 10% margin of error, -0.1 to 0.1, whatever it is. And then I'm going to take that margin of error and or that value of x, and just as I did before, add it to the pole, and that gives me my my noise up or down. Okay, and lo and behold, it's the same type of thing that we saw before with craps, where if we're planning code well and we're using modularity wherever we can and thinking about splitting it well, I'm doing this n times, so I need a for loop, and I'm going to use a subroutine that does it once, and that subroutine will delay the add noise function until later, and then I can handle the details. But all of a sudden, we actually have written on the level of pseudocode everything that we're going to need to simulate this election. I will provide polling data next time, and we're going to be able to implement the simulator. We'll start with kind of, let's implement the crap simulator first and see how quickly we can compute a house edge. And then we'll take the next step to implement these and look at our election simulator, simulate election once, and build in the add noise function. And you'll see that in a relatively short amount of code, we'll be able to, based off of different times that we actually pulled polls from for this 2016 presidential election, we'll be able to produce estimates for the forecast probability of each of the two candidates winning at those 3 times. So it's an exciting thing to do, and what's particularly exciting about it is it's a simple model. It allows us to see that there could be some sophistication with what's going on here, but really we can get a pretty decent idea of how it works with a short amount of code. And then the critical part of this is that we'll be able to then step back and reflect on the nature of Monte Carlo simulation, as well as how it applies to this particular example. Is the simulation a good thing for this particular example of forecasting an election? What are its strengths? What are its weaknesses? That type of thing is always fun to dig into as well. So that's what we'll do next time. For now, I'll just summarize. We've done quite a lot in a relatively short amount of time, and partly that's because we're focusing on the details of problem solving with respect to pseudocode without focusing on any specific implementation details, and we can do quite a lot if we do that. So again, what have we seen? We've seen that pseudorandom number generation is a trickier problem than it seems, and that even if we take a few minutes to pause and reflect on that, we have the appreciation for it, and that it's still relevant today. We saw how to leverage Monte Carlo simulation to build a crap simulator, or to compute the house edge of really any binary game, and we could generalize from there. If you wanted to do blackjack and you had a table, for example, you could see verify what the house edge for that given strategy is, try this for many simulations, and figure out what the best table of strategies is to begin with. Kind of the sky's the limit there. And then thirdly, we saw how we could apply these techniques to simulate a US presidential election or any election from state polling data. And next time we'll tie all that together. And otherwise, yeah, I look forward to that. So until then, I'll see you.